In this video tutorial, we're going to take what you explored on the particleadventure.org and translate the key points onto this note sheet. Take your time with this, stop it if you need to digest some of the information, and think of questions that you might have. This is very abstract, but once you get the general idea of the layout of the land, it should be straightforward. Okay, so we're going to start with what we did at the very beginning in this idea of fundamental. Okay, we're looking for the basic building blocks of nature, and we know it's more than just a proton, electron, neutron that we learned from chemistry. So let's make sure we understand what fundamental is, and it's any, usually tiny piece of matter, okay, that is not made up of smaller particles. Okay, so we mentioned basic building blocks in Legos. You get to the smallest piece, you can't break it down any further unless you actually break the Lego, which you're not allowed to do in nature. So we can ask questions of familiar particles. Are they fundamental or not? And if not, what are they made up of? Well, an electron is fundamental, okay? It cannot be broken up into anything smaller. As best all our experiments have never shown any substructure to an electron. A proton and neutron, which are also part of an atom, turn out to be are composite. They're made up of smaller things, and those smaller things are called quarks. In fact, they're made up of up and down quarks. Now, you don't have to know that for now. We'll talk about that in a little bit. Turns out there's different types of quarks, but if you want to take a proton, you can break it down into smaller parts. Electron, you cannot. Nucleus, well, what is a nucleus of an atom? Well, it's nothing more than protons and neutrons. So if it's made up of a certain number of protons and a certain number of neutrons, then of course it cannot be fundamental. It's a composite particle. An atom, well, an atom is a nucleus with electrons surrounding it. So that's the nucleus plus electrons. Well, then that's not fundamental. Okay, so that's the basic concept behind that. Now let's go to something we're very familiar with. Molecules. We know that the formula of water is H2O. And if you go back roughly 200 years, it was thought that the basic building blocks couldn't be broken down any further. Were 2 atoms of hydrogen and 1 atom of oxygen. Well, that's true in the sense that H2O is 2 atoms of hydrogen and 1 oxygen, but the atom itself can be broken down further. In the 1900s, we found that that's made up of protons, electrons, and neutrons, and for water, it's a specific numbers. So if we ask the question today, water would be considered to be comprised of what 2 types of fundamental particles? Well, if we go to 1900s, protons, electrons, neutrons, are those fundamental? We've already answered that. Electrons, yes, so that's fundamental, but not protons and neutrons because they're made up of something smaller, and that something are quarks, as we mentioned earlier. Okay, so notice how our vision of molecule has changed. It's gone from 2 types of atoms to 3 types of atomic particles to 2 types of fundamental particles. Now we could ask the same about salt. Is table salt made up of electrons and only quarks? Well, what is sodium? Sodium is an atom made up of protons, electrons, and neutrons. Chlorine is protons, electrons, and neutrons. Electrons are electrons. Protons and neutrons are protons and neutrons. They're made up of quarks. So a salt crystal is made up of only electrons and quarks that combine to make other particles that we just mentioned. So any compound, and therefore any cell, anything that's made up in our everyday world must be made up of quarks and electrons. Okay, that's really, really important. So we can ask, do any other subatomic particles exist? Are there only quarks and electrons? The answer is actually no. Okay, there are other particles that exist. It turns out there's roughly 200 of them. There's a whole particle zoo out there, most of which doesn't last long enough for you to notice because we're interested usually in atomic matter, which again is made up of 2 types of quarks and electrons. Okay, and of these 200, almost all of them are composite. Okay, meaning they're made up of a combination of fundamental particles. We'll talk about a few of them, but you don't have to know them. There's something called the rho or the z or the lambda. These are combinations of quarks, the ones I'm underlying. Okay, so we'll see quarks can combine to make all sorts of exotic particles. And then there's some fundamental ones called muons and neutrinos, which are very different altogether. So let's take our basic idea that all matter is composed of two classes of particles. Quarks, which we just mentioned, and then leptons. All right, so lepton is a brand new word. We'll look at the difference between the two, but if we make a little tree or branch in a tree, if we have matter, we want to understand the difference between those stuff made up of quarks and those that are made up of leptons. And then this all combines to all the familiar things that we've learned in chemistry and elsewhere. Okay, so let's start with quarks. It turns out that there's not just one type of quark, there are 6 types of quarks. And they can be categorized. They can be put in a structure much like the periodic table. We can go from generation 1 to generation 3, which goes from lightest to heaviest. And it turns out that they have an important property called charge. Okay, so I'm not going to write the names, I'm going to put the symbols. And these are in your reference table, so you don't have to memorize them. There is the up quark and the down quark. They were found first, early in the 1960s, if you're wondering. Very important that they're the lightest, and because they're the lightest, they're fairly stable, meaning they will last quite a long time. They won't decay into something else. Generation 2 quarks were found in the 1970s and the 80s. You don't have to know this, I'm just giving you a little background. They're called the charm and the strange quark. The generation 3, which are by far and away the heaviest, were found in the 1990s, maybe the aughts. Okay, that's called the top and the bottom. So we're going from lightest to heaviest. And the reason we put them in this order is because the up, the charm, and the top, those are the first row, have a particular charge. They are all positive 2/3. Okay, whereas the down, strange, and bottom happen to have a negative 1/3 charge. So that's kind of unusual in that we have fractional charge. You haven't seen that before. If you think back to chemistry, an electron is -1, a proton is +1, and a neutron is neutral. So here we can actually have fractions of charges. And when we put those fractions together we'll get integer numbers, as we'll see later on. All right, so let's continue on. So let's look at other facts about quarks, things that you want to know about them. Unlike protons and electrons, quarks have a very unusual property, and they are never, ever found as solitary or individual particles. You will never see an isolated up quark by itself or a strange quark zipping through space or an atom. All right? They are always always combined to make composite particles. Okay? So we might see a particle that's a combination of an up and a down, or an up, a down, and a strange, or a bottom, bottom, bottom. Okay, those are all allowed, but they're always combined together. I can't rip them apart to have a separate up, and a separate down. Now, why that happens is fairly complicated. You might ask, well, how do we know about the individual quarks? We've never seen an individual one. That's a really good question. We'll address that in class. But for right now, accept that quarks are never isolated. They're always composite. Okay? And now, therefore, any type of composite particle made up of quarks is given a special classification. That's called a hadron. Okay, an unusual name. It means something in Greek. I don't remember what it means. But a hadron is the name given to anything made up of quarks. And there's 2 varieties of hadrons, even stranger names. There's a baryon, and then there are mesons. Okay, mesons mean middle, mass, middlings. Baryons, I'm not sure what they mean, but here's what you have to know about them. Again, you see them in the reference tables. A baryon is any particle that consists of 3 quarks. Quark, quark, quark. That could be an up, an up, down, strange, a bottom, top, charm. It doesn't matter. Any 3 will be considered a baryon. Or it can be 3 antiquarks, and we'll talk about what antiquark is, but an antiquark is a symbol of a Q with a bar over it, Q with a bar with it, Q with a bar over it. Okay, mesons, on the other hand, consist of quark-antiquark pairs. So there's 2 quarks. One is a quark and one's an antiquark. So we give it the general symbol Q, anti-Q. So that could be an up and an anti-strange. Or that would be one particle. Let's say it's called a kaon. And there could be an up and an anti-up. That might be called a pion. All right, there could be other combinations. All right, we'll look at those more, but understand that that is just 2 ways that quarks can combine. And here's a very important rule that goes along with it. I don't have a line for this, but they always combine so that the charge is an integer. That's important. So those two types of quarks, mesons, or those two types of hadrons, mesons and baryons, are such that when you take any three of those quarks and you add up the charges, you will get an integer. 0, 1, -1, -2, +2. Okay, so for example, let's take a proton. We've already learned that a proton is a composite particle made up of quarks. Well, what quarks is it made up of? It turns out it's made up of the lightest quarks, because those are the most stable, but they're not just an up, up, up. It's an up, up, down. Okay, so the fingerprint of a proton, it distinguishes it from all other composite particles, like a lambda or a delta particle, are these three quarks. And if I look at the charges, an up is 2/3, another up is 2/3, and a down is -1/3, as we saw from our chart. If I add them up, you can do the math. Hopefully you see that that's +1, as we'd expect for a proton. A neutron, we know, is going to be neutral. It's also made up of quarks. It's got to be a different combination of quarks. Like the proton, it's made up of the simplest quarks, the ups and the downs, and it turns out to be an up, down, down. Okay, convince yourself how that can be a neutron. Well, 2/3 plus a -1/3 plus a -1/3, and you can see that's 0. Now, if I had another particle that was, let's say, a charm, strange, if I add up the charges, I will get 0 as well. Does that mean that's a neutron? And the answer is no. Okay? This is an altogether different particle that just happens to have a charge of 0. So not all neutral particles are neutrons. A neutron is a neutron because it's made up of those three quarks. Okay, so in the few minutes we have left, let's look at the other branch, the leptons. Leptons are very different than quarks. Okay, and we'll highlight them. But for right now, let's name them. Like quarks, though, there are 6 of them, and they come in 3 generations from lightest to heaviest. The most important one for us is the electron. Okay, its heavy cousin is called the muon. This is the Greek letter mu. Okay, I'll write it out here, muon. And then the heaviest of them all is called the tau particle. Those are Greek letters. Okay, and what these 3 all have in common, they're identical, except that muon is heavier, about 200 times heavier, and the tau is even heavier, is they all have a charge of -1. Okay, now there's a bottom row to this. A very interesting little particle is called neutrinos. And there's an electron neutrino, there is a muon neutrino, and then there is a tau neutrino. This is the Greek letter nu, N-U. All right, that's not a V, but you can draw yours like a V as long as you recognize it. And what distinguishes neutrinos from the electron, the tau, muon, and the tau is that it has a charge of 0. Okay, so note that these are integer charges. And a very important distinction between leptons and quarks is that leptons, or the question is, do leptons combine to make composite particles, or are they always found alone? And the answer is this. Okay, electrons never, ever combine together. Written out. So they are the ultimate loner. Okay, you only find leptons by themselves, zipping through space or through an atom. Okay, so they do not make bigger particles like the quarks do to make hadrons. And of the 6 electrons found in ordinary matter, okay, well, excuse me, of the 6 electrons which are found in ordinary matter, atoms, well, atoms are protons, neutrons, and electrons. Protons and neutrons are in a different category, so that would leave an electron. Okay, so an electron is very different than a proton and a neutron for reasons. And by far and away the most numerous electrons is the neutrino. Okay, and it's by far and away the most difficult to detect. Neutrinos are very, very hard to find, but we have done a good job. Now, on average, it would take about a solar system worth of lead to stop a neutrino. All right, so we'll talk more about this in class. This is our introduction to the basic particles that make up matter. Come in with some questions. Hopefully you found this interesting.